So how many of you came by the interactive poster session that we had yesterday and saw some of this already? So a few of you have, looks like about 40% of you maybe. So we'll go in a little bit more in depth into why we're doing this for this presentation. So I'm going to be talking about data that's stored in tree structures. Now, trees are everywhere. For those of you who are sports fans, brackets, those are forms of trees. See who's playing who and who's winning and who's moving on to the next round of a tournament. You have trees in the form of how you save all of the data on your computer. Different files and folders and subfolders and so on and so forth. And then trees are used pretty much everywhere else in terms of classifying different forms of life and so on and so forth. And in general, trees exist because we're pretty good at understanding trees. They make sense to us. It's a hierarchy of ordering things. And so people have done a lot of work with visualizing trees. Most people have seen trees set up pretty much like this, almost like a family tree where you've got org charts and hierarchies. Other folks visualize trees through something called a tree map. Has anyone ever used a tree map before? So yeah, we got a lot of hands going up. So essentially it's a way to break down a large data set into its components. I don't remember what this particular data set is, but let's say it's a breakdown of the people that are here at this symposium and which state they're from. So this yellowish orange block might be all of the people from California, and then this block might represent people from Irvine, this might represent people from San Francisco. The larger the block, the more the people, so on and so forth. And so you can divide these up. And so that's great. But what happens when you need to compare lots of trees? You want to see how one tree differs from another. It's good for looking at a single tree, but when you have to compare them, it gets difficult. So just an example of this. So let's say you're collecting data and you've got lots of attributes. Some are numerical. So we've got like apples, oranges, milk, that's a product. We've got quantities and prices. Those are numerical variables. Then we have some categorical variables. And then these variables are going to change over time. Can you see that? So some of those variables actually were moving back and forth, and it's really difficult just looking at the tree or looking at the table to understand what's going on. So trees. A little bit more about trees. They're essentially nodes and values on the tree. So we have three different types of trees. We have something called a fixed tree. That's where you have the structure is very much set in stone. So we have like the state at the top, have the county in the middle, and then the third level of the tree might be the city. That's a tree. Then you have dynamic trees, trees where you can move things back and forth. So like gender, ethnicity, and age range. You could also order this by ethnicity, gender, and age range, or age range, gender, and ethnicity. You can move the tree around. Some trees allow you to do that, some don't. Then you have mixed, where you might have to have like the first order of the tree be very static. You don't move it around. Then you have other levels of the tree that can merge and move back and forth. Different types of trees. So each one of those types of trees has different challenges associated with it when you're trying to figure out what changes over time. So you have topology changes, where you have different actual topologies. So here we see this tree, it's got 3 levels, but this level comes down to the left and then it juts off to the right. This one goes just barely to the left, then it mainly goes to the right. That's a topology change. Then we have node value changes. So the topology changes, the topology stays the same, but these little values out on the ends, they change. Then you have values on all the nodes change, same topology as opposed to just the leaves. Then you have values on the leaves only, but different topology. And you have values on all the nodes, but different topology. So what's interesting is there's already been work done to look at these two types of trees changing. People have studied this in the information visualization world. People have also partly addressed ways to visualize values on the leaves changing with different typologies. However, what we've tried to do is address all of these changes. So how can we visualize everything in the tree changing at any point in time, whether it's dynamic or static, node, topology, leaves, what have you. And we've developed essentially two different types of visualizations to look at the difference in the trees. One is called a bullet visualization, or bullet glyph, and the other is called a stem view visualization. I'm going to go over both of those. So for the bullet view, we've got these little things that essentially look like bullets. And what we do is the height of each bullet represents the relative change. So like a percent of change or something like that. Then we have the color represents the actual change. And then the direction of the bullet represents the direction of change. So a positive increase or a decrease. And then we can outline the bullets with different colors to represent something being created in a tree that didn't exist before versus something being removed from the tree that didn't exist before. So lots of different changes all being represented by one little glyph. So if we look at this in terms of an actual tree and an actual data set, you can have one tree up here. It's got 3 levels, 1, 2, 3, and several different nodes coming off. And then tree number 2, and notice how in tree number 2, it comes down over to the left, and there's just one node popping off of this guy. This one has 2 nodes. The middle one has 3 nodes. This one also has 3 nodes. And the last one has 2 guys down here, but only 1. The diff tree, using this bullet visualization, uses all these bullets to show that, okay, there's a definite decrease in value over here. There's an increase in value on this over here. Over on this side, between this tree and this particular node was removed because it has black line around it. It lost 100% of its value, which represent like $22 or whatever. And then over here we have a node that was created. It didn't exist before. And so on and so forth. So diff tree. And then we created this interactive visualization that allows you to dynamically play around with these different bullets and these different nodes. So we show you 2 different trees. Then we show you the difference, and then we have other little sections of this chart that give you percentage of change, and then we show you like a distribution of all of the nodes, so you can see which things are outliers and which are changing, which are not. So just as an example, here in this particular diff tree, we're seeing these 2 guys right here. These are outliers. And over here in the in this diff scatter plot, you can see that they're outliers, or they're off on their own. So this particular bullet view was good for looking at one change in time. So you've got one tree compared to another tree, and that's it. But that wasn't enough. We wanted to be able to do more. We wanted to look at changes over long periods of time, divided up into various temporal segments. So maybe 1 year to the next year, or maybe 1 quarter to the next quarter, or maybe last 5 years to the next 5 years, or something like that. So we came up with this new visualization that we call the stem view. And it essentially looks a little bit like a bar chart on steroids, where what we do is we have a line that goes through the center here. It's hard to see, but there's a line right through the center. Anything that goes above that line is a positive change. Anything that goes below is a negative change. So the actual change is represented by colors. The relative change is represented by height, positive or negative. The width of the particular bar represents the ending value. So you went from one value to another value over time, and the width represents that ending value. And then we still use the outlining to tell you whether or not something was created or deleted. So it's hard to see, but there's a white outline around that guy, and there's a black outline around this one, where you've got created and removed. So our new visualization looks a little bit like this, where what we have is the stem view in the center, where you've got your 3 levels of the tree, and you can actually add and remove levels. So this could be a 4 or 5 level tree or a 2 level tree, what have you. And then on the left, we're showing you how the particular values over in this tree have changed over time. So this top level is growing over time. This is the U.S. federal budget. So we see overall from 1970 to 2012, the U.S. budget has been growing and growing and growing. Then below that, we have different departments. So we have the Department of Transportation, we have the Department of Defense, and so on and so forth. And we can see which departments have increased their budgets or decreased their budgets from one year to the next, and you can choose what temporal range you want. And then underneath the department, you have the bureaus. So the Department of Transportation has Federal Highway Administration, it's got Federal Transit Administration, and I actually don't remember all the other groups, but there's lots of different subgroups under U.S. Department of Transportation that all have their own budgets. So all of that can be the third level of the tree. So the cool thing about the bullet versus the stem is one, the bullets, while they look really nice for small data sets, when you start to get into large data sets with lots and lots of nodes, it gets a little messy, because not only are we showing you the individual bullets, but we're trying to draw lines in between all of them, whereas in the stem view, everything is kept in this little container. So everything under this grouping is related to the one above it. You don't have all the lines going all over the place. It also makes labeling a little bit easier, though labeling is still a pain, this sort of stuff. So the tool is very interactive. It's not that you're just looking at a data set and that's it. There is a whole series of legends and reporting topologies and tools and all sorts of other stuff that are happening on the side. So what we do is we actually look at the tree and we look for exciting things that we notice that are changing in the data. This is all done automatically, just using some basic statistics. And so we go in, and this is a call out here, but we're showing you how many nodes existed on both trees, how many nodes were removed, how many nodes were created. Then we give you the absolute overall change, and we give you the relative overall change, and it keeps going and going and going, and we point out like certain nodes that increased more than others. Are there any outliers, or so on and so forth? And all of that is right there on the side of the screen, so you don't have to necessarily go visually inspect everything. But if you see something that's cool, all you have to do is take your mouse over and put your mouse over top of that particular report feature, and then everything else that is on the visualization disappears. And we just highlight those particular nodes that are called out in the report on the right-hand side. So it helps you identify those important changes that you care about. We've also integrated a nice filtering tool on the side, so you can go and say, I only care about nodes on the tree that changed by some sort of amount, relative or absolute, what was the starting value versus the ending value. You can do all these different slider bars, and just like with the previous hovering over here, it then gets rid of all of the nodes except the nodes you care about, and it highlights them on the tree. So we've done a lot of different case studies to try to go out and talk to different user groups to see how well the tool actually works for them. We met with the Food and Drug Administration to look at adverse drug effects on people. So that was a relatively small data set. We also looked at the National Cancer Institute to look at lung cancer death rates over time to see if there's any patterns or outliers that we should be concerned about. We also went to the U.S. Department of Transportation and we looked at passengers that are flying in the U.S. on various carriers and various airports. The University of Maryland has been using the tool to take a look at students' enrollment rates in various classes and trying to look at how enrollment rates changes over time. And when I say over time, I mean day to day, week to week, just to see if certain press releases that professors are putting out about classes is having any sort of effect on enrollment whatsoever. We also looked at the U.S. federal budget. That's what I was demoing a lot yesterday outside. Everyone understands a budget, so that's the easiest thing to show. And I actually was not a part of the IDB thing, so I don't even remember what that was. And then we also looked at traffic bottleneck data. So Michael Van Daneker just went and showed you that we have the capability to look at an entire state or county or whatnot. Well, what we tried to do here is we tried to look at every county in every state that we had data for over X number of years and try to visualize that. So I'm actually going to go, and I cannot do a live demo of the tool in this room because we are stuck with 1024 by 768 pixels, and this requires HD. So everything just gets squished. So instead what I'm going to do is show you a video that we've compressed to fit on the screen. It's a 3-minute video that overviews how you can work with the tool, and we're going to show you that with passenger data.
In this demo, we're going to use TreeVersity to analyze the change in the total number of passengers flying in the US between 1990 and 2003. Here on the left, we can see a timeline showing the overall change of the number of passengers. That is showing us that between 1990 and 1991, there was an increase of 15 million passengers. We move to the next year, we see that there's a new tendency of increases between 91 that extends all the way up to 2001.
So he's moving forward in time, showing 2 years.
Include more elements from the data set provided by the Department of Transportation to say include the origin state from which the passengers took off. By doing that, we get a new hierarchy that will add a new level here to the TreeVersity and will show us all the different states with the total number of passengers and the changes by state. Each one of these boxes shows the change by state. Boxes going up or in green colors show increases, like here in California, and boxes going down, like this one in North Carolina, or in yellow and red colors show decreases. The height of the boxes shows the percentage of change. The color is the actual number of passengers changed, and the width of the boxes shows the ending value for the different
Notice
states.
when he's hovering over in the box,
it's California
that
is the
field
biggest
over
state,
here.
which is corresponding to the biggest timeline on the left. And then if we follow the second timeline, we see that Texas is the second state, followed by Florida, at least in total number of passengers. We continue the analysis by years. We see that overall there are many years in which some states are increasing and some other are decreasing, but if we continue all the way the tendency to 2001, we see that in that year there was a big decrease in the total passengers. This was due to the attacks of 9/11, which the passengers were afraid to fly in the US, and there were some regulations that stopped the number of passengers. And we see that reflected in the total number of passengers flying by state. However, we focus our attention to this green box here in the middle. We see that there's at least one state, that is Maryland, that actually increased the number of passengers. We zoom into Maryland, we see that Maryland actually increased in 432,000 passengers. That is a 4% increase between 2000 and 2001. To add a little bit more of information, we can add also the origin cities. from which the passengers took off. And then we will have a new layer in TreeVersity that will show us a little bit more of details of where the passengers came from. We see that Baltimore, as the city providing the biggest number of passengers in Maryland. Zooming back out to the overview, we have now three levels, one for the overview to the passengers for the origin states, one for the cities. And we see the biggest cities here being Los Angeles, Atlanta, Chicago. We have the timelines for them, and we see changes for each city. You see that, again, that most of the cities are decreasing, but there are some green boxes that are actually increasing. To focus on those, we can add a filter that says to show only those things that are increasing. To do that, let me create an absolute difference filter, remove the bidirectionality option, and then add that we only want things between 0 and 48 million passengers, at least in change, and then we enable it. When we do that, notice that all the other cities disappear, and now we have only the increasing cities. We see that Baltimore is one of the biggest ones. Pittsburgh is also quite big in terms of the total number of passengers. But then there are some states like Florida, we zoom into that, in which some cities like Fort Lauderdale, Fort Myers, West Palm Beach, and Palm Beach, all of them are increasing in the number of passengers, but the state overall is decreasing. That is shown here with the yellow to red colors in the middle.
All right, so I know the audio kind of sucks, but the point was to show you the interactivity within it. And notice that there's a lot of animations. Anytime you click on something, things move about, and you're able. That's not just to make it pretty, just to show how fancy we can be. The idea of showing the animations is to help your eyes follow the data points that are moving, so you don't become lost. If everything just switched all of a sudden, you wouldn't know what switched. You want to see it move around. If you go to YouTube and search TreeVersity, you will find all sorts of videos that we put online that talk about various data sets. So example number 2, traffic bottleneck data. So I was talking about earlier, so moving forward with what Michael Van Daneker was talking about. These are just some screenshots, but what we have here is essentially all of the bottlenecks added together at the top for the all of the states on the East Coast. Then we have a listing of all of the states, and then we have all of the counties within each of the states. So all of these guys right here are North Carolina counties. All of these guys right here are South Carolina counties and Virginia counties, and Maryland is in there, and so are a few other northeastern states. So you can move forward and backwards by month, by year, what have you. And notice right off the bat, what you see is that something's going on in North Carolina. Congestion was getting significantly worse between March and April for some reason. And if we look below that, we can see that Haywood County is really bad. And so we can click on North Carolina, and that would then zoom in. We see Haywood is so much bigger than all the other counties. And when I was showing this to the folks in North Carolina, they said, oh yeah, well that makes sense. It was because I-40 in North Carolina experienced this massive landslide. They often have landslides out there, but this one was particularly large. And it took them quite a long time to fix it. And this is a popular road that a lot of people want to drive on. So what happens is, instead of going here in Tennessee along I-40 to get in North Carolina, they then told everyone that here's one detour that goes through the county, or you can go all the way up 81 and come down around here. So we saw congestion increase significantly on these other roads instead, and those are in that particular county that experienced all of that awful congestion. So we actually went out and we did user testing with all of the groups that I showed you earlier, and we essentially sat down with them, gave them one-on-one training with the tool, because it's not super intuitive. It takes a while to kind of get in the frame of reference of understanding where all these bars are. So we helped them out, did a little bit of hand-holding, and then we released them to do their own analysis with the data. And after they had experimented with it for a while, we just went and asked them some simple questions. So, for your particular data set, was TreeVersity useful? Was it not useful? Was it extremely useful? Are you likely to use the tool again? Did you understand it, or did you really need us to come back and help you more with it? Would you want to continue working with it? And so on and so forth. And for the most part, all of the agencies expressed some excitement in TreeVersity and were able to identify things that would have been a little bit more difficult to identify just by using typical SQL queries and whatnot. So that's really it. I think a lot of you saw the tool yesterday. We'll be around during the break. Feel free to come up to us. We can actually show you the tool on our computers in live mode where we've got more pixels. And he's not here, but I would like to thank John Guerra Gomez, who was the principal investigator for this project for the CATT lab. He did a really good job. So thank you very much.
Questions?
If we wanted to get a copy of TreeVersity.
So we generally don't provide our code to anyone. However, we are working on a new version of TreeVersity. It's probably 9 months out, but that version will allow you to actually go and upload your own data set to the tool. So you wouldn't have access to the code, but you'd have access to the tool and be able to do your own analysis.
Pat?
So basically, you're having a program now where you're, like, DOT or whatever is a customer, and they come to you to get trained in TreeVersity, or how does this work?
Well, so this is very much a research tool. We don't have an end game in sight. So we don't really provide training. If someone is really hot to trot on a tool, we'll help you out. We have put a few videos up that help with some training, but I don't really know where we're going with it. This doesn't currently have funding. The CATT Lab is blessed in that some of our sponsors, Maryland State Highway in particular, gives us a significant amount of funding each year, and 20% of that funding is for whatever we want to do. And so we have these little pet projects that we play around with, and sometimes they work out, sometimes they don't. But we don't have any additional funding going forward with this. We'll just kind of work on it in skunkworks as we're able.
Pat, you had a question?